The desire for realistic-sounding audio in virtual environments has increased in recent years, particularly with the rising popularity of VR. There are a wide range of approaches that can effectively model sound propagation, the most common of which is to adapt a computer graphics technique known as ray tracing to model the propagation paths from source to listener as a set of discrete rays. These techniques can quickly become computationally unfeasible to run at interactive rates when either scene complexity or the number of rays emitted is high. This project, whilst primarily concerned with implementation, aims to uncover user perception of different input geometries and different numbers of emitted rays. Our software, created as a Unity native audio plugin, accounts for frequency-dependent propagation behavior by splitting the input signal into a number of subbands. Virtual environments are typically made up of lots of polygons. For example, in the scene shown here, there are over 400,000 triangles. Our software allows simple selection of objects to be included in the sound propagation calculation, making it easy to use a simple box representation or a more complex version of the virtual environment. The ray tracing algorithm is primarily concerned with finding where a ray will reflect in the given scene. The triangles are stored in an acceleration structure called a bounding volume hierarchy. This recursively splits the scene's triangles into smaller and smaller bounding boxes. This means the intersection algorithm can quickly cull a large number of triangles by performing tests with these boxes, resulting in substantially fewer calculations. During path calculation, the length and absorption of each ray is stored. Rays are automatically culled if they exceed a predefined path length or total energy absorption is too low. The software can easily vary the number of rays emitted from the sound source. Once all paths have been calculated, an impulse response for direct sound and early reflections is created, depending on each ray's path length and total absorption. From this impulse response, we calculate a statistical model for late reverberation by using backward integration of the Schroeder decay curve. The input audio can then be auralized using convolution with this impulse response. Our tests ask subjects to describe the scenes in terms of size, emptiness, and material only by listening to audio clips. We varied the number of rays and input geometries. They were also asked to select the most appropriate sound clip after being shown the scene. Primary results show that the number of rays do not matter for reflective environments, and that simple approximations of the virtual environment may be valid.